ever get that feeling? Like, you really want to understand something complex. Like, you want to be in the know, but without, like, drowning in a sea of details.
Yeah, I know exactly what you mean.
Yeah, well, that's kind of what we're doing here, right? We're trying to, like, cut to the chase.
To get to the heart of the matter.
Exactly.
Yeah.
And today we're taking a deep dive into Multicast.
Multicast.
Yeah.
It's a technology that at its core tries to solve a really fundamental challenge, right? Like, how do you get information to a lot of different people at the same time, but do it efficiently?
Right. And so we've been pouring over a whole bunch of stuff on Multicast.
Oh, wow.
Yeah, a whole bunch of stuff.
You guys have done the hard work?
We've done the hard work, yeah, so you don't have to.
That's great.
Yeah, we went through all the boring stuff and try to pull out the exciting bits.
That's right.
So our mission here is to basically, like, extract the most important concepts and advantages.
Yep.
And even, like, some of the cool tricks behind Multicast and explain them in a way that's hopefully clear.
Yeah, it just makes sense.
Yeah.
Right.
So let's get right to it. What is Multicast?
Multicast.
Yeah.
So at the essence...
yeah, like, let's unpack this a little.
Yeah.
Let's imagine I need to send the same file to 10 different colleagues.
Right.
If I'm doing, like, the regular one-to-one, which is Unicast,
Right.
then I'm sending the same file 10 different times,
Yeah.
and that's clogging up the network.
Exactly. Yeah, you're just consuming so much bandwidth.
Yeah. So Multicast is different.
Yeah.
It's like sending one copy, and then the network itself intelligently distributes it to only those who need it.
To only the interested receivers?
Yeah.
And that is where the huge scalability benefit comes in.
Right.
Yeah.
So like, if you imagine, like, a company-wide video broadcast,
Right.
if you were to do that with Unicast, you'd be sending the same stream.
To everyone.
Yeah. Hundreds or thousands of times.
Yeah, it would just cripple your network.
Yeah, it would just be a mess, right? But Multicast solves this really elegantly.
Yeah, very efficiently.
Right. So for things like live streaming and distributing software updates
Yeah.
to, like, a large organization.
Yeah, any kind of large-scale content distribution.
Multicast is just like a total game changer for efficiency.
Huge efficiency gains, yeah.
But it's not like magic, right?
Yeah.
You can't just, like, sprinkle Multicast dust and then everything just works.
Yeah, it's not something that just works out of the box.
Right.
There are two key elements that need to be in place
Okay.
for Multicast to function properly.
Why?
The first is that the applications that are sending and receiving the data need to be multicast aware.
Okay, so the applications themselves need to understand it.
Yeah, they need to be able to speak multicast, so to speak.
Okay.
And the second is that the network infrastructure itself,
Right.
the routers and the switches,
Yeah.
need to be configured to be able to handle this multicast traffic.
Right.
Yeah.
So they need to know where to send these group transmissions.
Exactly.
Yeah. And this brings us to multicast addressing.
Right.
Now, this isn't like your regular IP addresses, right?
No.
It's a little different.
Yeah, it uses a special range of IP addresses,
Okay.
which is called Class D.
Okay, Class D.
Yeah, and this is the range from 22.4 to 239.255.255.255.
All right, so it's like a reserved set of IPs specifically for identifying groups of receivers.
Exactly, yeah. It's for groups, not individual devices.
Okay, and within that special block, like, are there different sections that are reserved for different purposes?
Yeah, so the INA, the Internet Assigned Numbers Authority,
Right.
has carved out specific ranges within that Class D block
Okay.
for different uses.
Right.
So, for example, the range 224.0.0.0.0.0.0.0.255
Okay.
is reserved for network protocols themselves.
Right, so that's for the network's own kind of behind-the-scenes communication.
Exactly. Yeah, it's for communication between networking devices within a local network.
Right.
And these addresses are generally not forwarded by routers to other networks.
Okay, so that's all local.
Yeah, it's all contained within that local network.
All right, so what about when we actually want to use multicast for applications like sending a video stream?
Right. So for application level uses, INA has also allocated the 224.0.1.024 block.
Okay.
And the key difference here is that traffic destined for addresses in this range can be routed across different network segments.
Right.
So it allows for broader distribution.
So like a live video feed being sent to many viewers
Yeah.
might use an address in that routable range.
Right.
Now, one thing that seemed important from all the stuff we read is that these multicast addresses are purely for the destination.
That's right.
So the device sending the multicast still uses its regular individual IP address as the source.
Exactly. Yeah.
So it's like the return address on a piece of mail.
Yeah, that's a great analogy.
Yeah.
Yeah, so if you were to look at a multicast data packet,
Yeah.
The IP address in the destination field would be one of those Class D addresses,
Right.
identifying the intended group of receivers. But the source IP address would be the regular unicast IP address of the device that originated the traffic.
So like the regular IP address of my video streaming server.
Exactly.
Okay. Yeah,
So it's just coming from a regular device,
Right.
but it's going to a special group address.
that clarifies things.
Yeah.
And you mentioned needing applications that are multicast aware.
Yes.
Can you give us a tangible example of that? Like something people might actually use?
Yeah. So a very common and accessible example is VLC, Media Player.
Okay, VLC?
Yeah. So VLC can both send out a video stream to a specific multicast address
Okay,
and receive a stream from a multicast address.
got it.
So it's a really practical way to see these kind of abstract concepts
Yeah.
actually being used in everyday software.
Okay, so we have a source sending data to a multicast address.
Right.
Now, how did the network devices,
Yeah.
and in particular the routers, how
Yeah.
do they figure out which specific devices want to receive this traffic?
Right.
They can't just broadcast it everywhere. Because that kind of defeats the purpose.
Exactly. Yeah, it would just be regular broadcast then.
Right.
So this is where IGMP comes in.
Okay, IGMP.
Yeah, the Internet Group Management Protocol.
Okay.
And you can think of IGMP as the mechanism that allows devices on a network,
Right.
so your computer, your smart TV,
Yeah.
to tell their local router,
Okay.
hey, I'm interested in receiving data that's sent to this particular multicast address.
So it's like subscribing to the multicast stream.
Exactly. Yeah.
Yeah.
It's like hitting the subscribe button.
I like it.
Yeah.
So individual devices use IGMP to signal their interest
Right.
to their local router.
Yeah.
So how does the router then use this information?
So using those IGMP messages, the router can build up a picture of which of its connected network segments
Yeah.
have active listeners for specific multicast groups.
Okay.
So when the router receives multicast traffic,
Right.
it knows exactly which of its outgoing connections it needs to forward that traffic on.
Okay.
And that avoids unnecessary flooding of the entire network.
Right. So it's like the router is saying, okay, these folks over here signed up for this channel,
Yeah.
so I'm going to send it that way.
Exactly, yeah.
Now, we also looked at the role of network switches in all this. So
Right.
they
Yeah.
sit between the source and the end users
Yeah.
on the local network. So they must be involved in managing multicast too, right?
Yeah, absolutely.
Okay.
So while routers handle the routing of multicast traffic between different networks,
Right.
the switches within a local network segment,
Yeah.
they also need to be intelligent about how they handle multicast traffic.
Okay.
Because if a switch just sent all multicast traffic out of every port,
Right.
it would just create a lot of unnecessary traffic on that local network.
Yeah.
And that can potentially slow things down for everyone.
It would just become a bottleneck.
Exactly.
So how do switches avoid becoming multicast bottlenecks?
So the key technology here is IGMP snooping.
Okay.
You can imagine the switch kind of listening in on the IGMP conversations that are happening between the devices on the network and the local router.
Okay, so it's eavesdropping.
Yeah, it's eavesdropping, basically.
So I like it.
By snooping on those messages, the switch learns which specific ports have devices
Yeah.
that are interested in particular multicast groups.
Okay.
So you can think of the switch's CAM table.
Cube table.
Yeah, as like a really fast address book
Okay.
that links multicast group requests
Okay.
to specific ports.
Got it.
Yeah.
So let's say a device on the network joins a multicast group using IGMP.
Yeah.
What does the switch do with that information?
So when a device sends an IGMP membership report,
Right.
essentially saying, I want to join this multicast group,
Okay.
the switch intercepts that message.
Okay.
And it adds an entry into its CAM table.
Right.
And that entry creates a link between that multicast group address and the specific port on the switch where the requesting device is connected.
Okay, so it's learning, basically.
Exactly. Yeah, it's
Yeah.
learning which ports need which multicast traffic.
Got it. And what happens when a device wants to leave a multicast group?
So when a device sends an IGMP leave group message,
Okay.
the switch will intercept that message as well.
Right.
And it will look up the corresponding entry in its CAM table
Right.
and remove it.
Okay.
And that ensures that the device that left the group no longer receives the multicast traffic for that group.
So it's basically unsubscribing.
Exactly.
Okay.
It's like hitting the unsubscribe button.
That sounds much more efficient than just like blasting the traffic everywhere.
Yeah, much more efficient.
Okay.
Yeah.
But what if a switch doesn't implement IGMP snooping at all?
Right.
What happens then?
So without IGMP snooping, The switch has no way of knowing which devices are actually interested in the multicast traffic.
Right.
So in that scenario, the switch will default to flooding,
Okay.
which means it sends the multicast traffic out of every single port on the switch, just like it would with a regular broadcast.
Okay.
And that can quickly lead to network congestion and a poor experience for users.
So IGMP snooping is really critical for keeping that multicast traffic contained
Yes.
through only the relevant parts of the local network.
Exactly.
Okay, now how does the switch figure out which of its ports is connected to the upstream router that's feeding it the multicast traffic in the first place?
Yeah, that's a great question.
Yeah.
So the switch needs to identify what's called the M route port.
M route port.
Yeah.
Okay.
Which is the port that leads towards the multicast-enabled router.
Okay.
And it does this by listening for specific, well-known MSE addresses that are associated with multicast routing protocols,
Okay.
such as PAM, which we'll talk about shortly,
Right.
and also by observing the IGMP query messages that originate from the router.
Right. So the switch is not just passively observing the devices.
Yeah.
It's also actively looking for signals from the routers.
Exactly.
Interesting. Our sources also briefly mention CGMP.
Yes.
What is that in relation to IGMP snooping?
So CGMP stands for Cisco Group Management Protocol, and it's a Cisco-developed protocol
Right.
that serves a similar purpose to IGMP snooping.
Okay.
It allows the router to explicitly tell the switch
Sure.
which ports should receive multicast traffic for specific groups.
Okay.
However, IGMP snooping has really become the more widely adopted
Right.
and standard method for layer 2 multicast management.
So it's more universal.
Yeah, it's definitely the more common approach these days.
Okay, so IGMP snooping is like the way to go for switches to handle multicast.
Yeah, I would say so.
Okay.
Yeah.
Now let's move up to layer 3
Okay.
and look at multicast routing protocols.
Right.
So we saw a few different names, DVMRP, MOSPF, and PM.
Yes, those are the protocols that routers use to determine the best paths for forwarding multicast traffic
Right.
across different networks.
Okay.
So DVMRP stands for Distance Vector Multicast Routing Protocol.
Right.
And MOSPF stands for Multicast Open Shortest Path First.
Okay.
These are both older protocols,
Okay.
less commonly used today. The one that you'll encounter most commonly today is PIM.
PIM.
Yeah, Protocol Independent Multicast.
Okay. Protocol independent multicast.
Yeah.
That sounds interesting.
Yeah.
What makes it protocol independent?
So the protocol independent aspect of PIM refers to the fact that PIM doesn't build its own separate unicast routing tables.
Right.
It relies on the unicast routing information that's already established by other routing protocols,
Okay.
like OSPF, EIGRP,
Yeah.
or even static routes.
Okay.
So it's independent of how that unicast routing table is created,
Right.
but it absolutely needs one to function.
Got it.
And this is a key difference from those older multicast routing protocols that we mentioned, like DVMRP and MOSPF.
Okay, so it's piggybacking on the existing infrastructure.
Exactly. Yeah, it's leveraging what's already there.
Right. That makes sense for efficiency.
Yeah, definitely.
Now, when we looked at IGMP again, we saw that there are different versions.
Yes.
V1, V2, and V3.
Right.
What are the main differences and like what improvements came with each version?
So IGMP v1 was the original,
Okay.
and it was the simplest.
Yeah.
It had only 2 core message types:
Okay.
membership reports,
Okay.
which a device sends to join a multicast group,
Right.
and membership queries,
Yeah.
which the router periodically sends to check if devices are still interested in the group.
So it's a basic, I want to join and are you still there?
Yeah,
system.
that's very basic.
What were the limitations of that initial approach?
So one significant limitation was in how a device would leave a group.
Okay.
So in IGMP v1, a device that wanted to leave a group would simply stop sending membership reports.
Okay.
And the router would only realize that the device had left
Right.
when it sent its periodic query
Yeah.
and didn't receive a response.
Okay.
After a certain amount of time,
So there was a delay.
yeah, there could be a delay
Okay.
in the router stopping the multicast stream to that device.
So IGMP v2 was developed to address this.
Exactly. So
Right.
IGMP v2 introduced a crucial improvement,
Right.
leave group messages. So now when a device wants to leave a multicast group,
Yeah.
it can explicitly send a leave group message to the router.
Oh, okay. So it's much more direct.
Yeah, it's much more explicit.
Okay.
And that allows the router to stop forwarding traffic to that device much more quickly.
Were there any other key enhancements in v2?
Yeah, so IGMP v2 also added group-specific membership queries.
Okay.
So if a router received a leave group message for a particular multicast group,
Right.
it could send out a query specifically for that group
Okay.
to see if any other devices on that network segment were still interested.
Right.
And this prevents the router from prematurely stopping the multicast stream.
Right, if other people are still listening.
Exactly.
Yeah. Okay.
It also introduced the maximum response time field
Oh.
in the query messages,
Right.
giving devices a specific time frame to respond.
Okay.
And finally, IGMPv2 formalized the process of querier election.
Querier election.
Yeah, where the router with the lowest IP address on a subnet takes on the responsibility of sending the IGMP queries.
Okay.
IGMPv2 is also often referred to as Any Source Multicast or ASM.
ASM.
Yeah.
Okay.
And that's because with V1 and V2,
Right.
receivers join a group
Yeah.
and they receive traffic from any source sending to that group address.
Okay.
They have no way to specify a particular sender.
Okay, so it's just whoever's sending to that group.
Exactly.
Okay.
Yeah.
Now, IGMPv3 brought in this concept of source filtering.
Yes.
This sounds like a big enhancement.
It's a significant advancement, yeah.
Yeah.
So IGMPv3 allows a device to not only join a multicast group,
Right.
but also to specify which specific sources
Okay.
it wants to receive traffic from for that group.
So instead of just saying, I want to watch the news stream on this address,
Right.
a device could say, I only want to watch the news stream on this address if it's coming from this particular server.
Exactly.
Okay.
Much more granular control.
Yeah, so it's much more specific.
Yeah.
What's the primary benefit of that source filtering?
So it allows for much more efficient use of network bandwidth.
Right.
And it can also enhance security.
Okay.
So receivers are only getting the traffic that they explicitly want from the specified sources.
Right.
And that reduces unnecessary load on the network.
Okay, so it's kind of cleaning things up a bit.
Exactly.
Okay.
And it's also a fundamental requirement for source-specific multicast.
Source-specific multicast or SSM?
SSM.
Okay, how does that relate to IGMPv3?
So SSM is a multicast delivery model.
Okay.
Where a receiver explicitly indicates both the multicast group it wants to join
Right.
and the specific source or sources it wishes to receive traffic from.
Okay.
So IGMPv3 is the protocol that enables hosts to signal this source-specific interest to the network.
Okay, so IGMPv3 makes SSM possible.
Exactly. Yeah, it's the underlying signaling mechanism.
Okay, you even had an example configuration, like
Yeah.
IGMP3 join group 239.1 on 1.1 source 1.1 point,
Right.
which shows how a device on a Cisco interface can join the multicast group 239.1.1.1,
Yeah.
but will only receive traffic originating from the source IP address 1.1.1.1.
Exactly. Yeah. So it's very specific.
So we've seen how individual devices signal their interest in multicast at the local level using IGMP.
Right.
Now, how does this interest translate into efficient routing of multicast traffic across larger network infrastructures?
Yeah. So that's where multicast routing protocols like PIM come in.
Right.
And there are two main modes of operation for PIM,
Okay.
dense mode and sparse mode.
Dense mode, sparse mode.
Yeah.
These sound like fundamentally different approaches.
They are, yeah. They're based on contrasting assumptions about where those receivers are located.
Okay.
So dense mode operates on what's called a push model.
A push model. Yeah.
When a router receives a multicast packet for the first time, it assumes that there will be interested receivers
Okay.
on most, if not all, of its downstream network segments.
So it's like the router is saying, here's the content, everyone gets a copy,
Exactly.
and if you don't want it, you can tell me to stop.
Yeah, that's a great way to put it. So it initially floods the traffic out on all of its interfaces, except the one it received it on.
Right.
And then routers on segments where there are no interested receivers
Right.
will send prune messages back upstream
Okay.
to instruct the originating router to stop sending the traffic down that particular path.
Okay, so it floods and then prunes.
Exactly, yeah, floods and prunes.
Okay.
The protocols that operate in dense mode include DVMRP, MOSPF, and PIM dense mode itself.
Right.
And so the fundamental choice between dense mode and sparse mode
Yeah.
really boils down to receiver density.
Okay.
So dense mode assumes that there's going to be a high density of receivers,
Right.
and it tries to minimize the initial setup
Okay.
by just flooding the traffic everywhere.
Right.
But that comes at the risk of wasting bandwidth.
Right.
There aren't actually that many receivers out there.
Okay, so dense mode is kind of like a shoot first, ask questions later approach.
Yeah, that's a good analogy.
Now, to prevent these initial floods from creating loops in the network, what mechanism is in place?
So PM dense mode and those other dense mode protocols,
Right.
they utilize reverse path forwarding, or RPF.
RPF.
Yeah.
Okay.
And you can think of RPF as the router checking the return address on a package
Okay.
to make sure it came from a legitimate sender on the expected route.
Right.
So when a router receives a multicast packet,
Yeah.
it examines the source IP address,
Okay.
and then it consults its unicast routing table
Right.
to see which interface it would use to send traffic back to that source.
Okay.
If the multicast packet arrived on that same interface,
Right.
then it passes the RPF check and it's forwarded.
Okay.
But if it arrived on a different interface,
Yeah.
then it's dropped.
Okay.
And that helps prevent routing loops.
So it's making sure the traffic's coming in on the expected path.
Exactly, yeah.
Okay.
It's verifying the path.
You mentioned that dense mode can be inefficient.
Yes.
Why is that the case?
So the inefficiency stems from that initial flooding.
Oh.
So even if only a small number of receivers are actually interested in the multicast stream,
Yeah.
the traffic is still initially sent everywhere.
Right.
And that can consume a significant amount of bandwidth
Yeah.
and processing resources on routers,
Right.
especially in large networks,
Yeah.
with many network segments
Yeah.
and only a few multicast subscribers.
Right. So you're wasting a lot of bandwidth.
Exactly.
Yeah. And you mentioned that this flood and prune cycle can even repeat periodically,
That's right.
like every 3 minutes in earlier versions of PM.
Yeah, so in PIMv1, for example,
Okay.
that flood and prune behavior happens every 3 minutes.
Okay. So it's continually flooding and pruning,
Yeah,
even if nothing's changed.
exactly.
Okay.
However, later versions of PM, like PIMv2,
Right.
they introduce mechanisms like state refresh
Uh-huh.
to make that pruning more persistent.
Okay.
So they periodically send prune messages
Okay.
to maintain that prune state.
So it's not constantly flooding.
Exactly, yeah. It's trying to be more efficient.
Okay.
And the resulting topology in dense mode is often called a source-based distribution tree, or SPT.
SPT.
Yeah.
Okay.
Or simply a source tree.
Source tree.
Yeah.
Okay.
Because the path is optimized from the source to each receiver that requests the stream.
Right. So sparse mode sounds like it takes the opposite approach.
Yeah, exactly. Sparse mode operates on a pull model.
A pull model.
Yeah.
Okay.
So it only forwards multicast traffic
Right.
to those network segments
Yeah.
where there are known interested receivers.
Right.
It doesn't flood traffic indiscriminately.
So sparse mode is for targeted delivery.
Exactly.
Okay.
Yeah.
So sparse mode requires more initial coordination.
Right.
But it saves bandwidth
Yes, definitely.
when only a fraction of the network actually needs the stream.
Yeah.
Okay, so how does sparse mode know where these interested receivers are located?
So sparse mode relies on a special router
Okay.
within the multicast domain
Right.
called a rendezvous point, or
Yeah,
RP.
right.
Yeah.
Okay.
And all multicast sources that want to send traffic to a particular group,
Right.
they first register their presence with the RP.
Okay.
Similarly, all receivers that want to join a multicast group for the first time,
Right.
they send a join request towards the RP.
Okay.
So the RP acts as a central meeting point.
So it's like a central switchboard.
Yeah, that's a good analogy
Yeah.
for sources and receivers.
Okay. So how do the routers in a sparse mode network know where to find this RP?
So there are a couple of primary methods for that.
Okay.
One way is that you can manually configure the IP address of the RP
Right.
on every router within the multicast domain.
Okay.
However, for larger and more dynamic networks,
Right.
that manual configuration can be quite complex
Yeah.
and prone to errors.
Right.
So a more scalable and automated approach
Okay.
involves using RP discovery protocols,
Okay.
such as AutoRP, which is a Cisco proprietary protocol,
Right.
or the PM bootstrap router, or
Ugh,
BSR.
It's R again.
Yeah, which is a standard mechanism defined in PIMv2.
Okay.
Yeah.
So let's say we have an RP configured or discovered.
Right.
What's the initial path that multicast traffic takes from a source to a receiver in sparse mode?
Okay, so when a source starts sending multicast traffic
Right.
to a particular group,
Yeah.
the first router that's directly connected to the source,
Okay.
which is often called the first hop router,
First hop router.
yeah, it encapsulates the initial multicast packets
Okay.
within a special PM register message.
PIM register message.
Yeah.
Okay.
And it sends this register message as a unicast packet
Okay.
directly to the RP.
Okay. So it's sending it as a regular unicast packet.
Exactly,
Right.
just to the RP.
Got it.
And when the RP receives this PIM register message,
Yeah.
it essentially learns that there's a source sending traffic for that multicast group.
Okay.
Now, if there are currently no receivers registered for that group,
Right.
the RP might send a PIM register stop message.
Register stop.
Yeah. Back to the first hop router,
Okay.
instructing it to stop sending that encapsulated traffic.
Heh.
If there are interested receivers, though,
Yeah.
the RP will acknowledge the registration
Okay.
and start forwarding the multicast traffic.
Okay.
And the RP might also periodically receive PMM register null packets.
Register null packets.
Yeah,
So.
from the source's first hop router
Right.
as a way to check if the RP is still interested in traffic for that group.
Okay.
And the RP will respond with register stop messages
Right.
if there are still no receivers.
Got it. So it's just kind of checking in.
Exactly. Host speaker.